So in our last class, we started by looking at your aromatic compounds, and under this we were looking at some of your reactions that your benzene undergo. So just to recap, your benzene is your 6-carbon ring structure. It contains your sp2 hybridized carbon, and throughout your entire structure you're going to have delocalized electrons. These delocalized electrons increase the stability of your benzene, causing it to be resistant to addition reactions. However, your benzene can undergo substitution reaction where an electrophile is substituted onto your benzene ring. Set of your examples, these were chlorination and bromination of your benzene. In this case, it's occurring at room temperature and you need a catalyst. If you're going to be adding chlorine, you're going to look at catalyst that contains your chlorine. So you have aluminum chloride and you have your iron chloride. If you're looking at your bromine, you're looking at your aluminum bromide and your iron bromide. So in both of these cases, your catalyst, in this example here, it's your iron 3 chloride. Catalyst, whether it's your iron 3 chloride or bromide, is going to be forming a bond with one of your chlorine atoms. Alright. So 2 electrons from this chlorine gets donated to your iron to form that bond. So when this molecule here comes in contact with your benzene ring, the chlorine that is closest to your ring is going to be carrying a partially positive charge, causing the bond between these 2 chlorines here to break off, giving you your very strong electrophile. This chlorine is now going to be forming a bond with one of the carbons in your ring. The other carbon is now without that 4th bond. So the addition of your chlorine or your bromine causes this double bond here to break, and your carbon that now has 3 bonds is carrying a positive or +1 formal charge. This is known as your carbocation. So in order for your benzene to gain back stability and reform this double bond here, a base or a negatively charged anion or a negatively charged species is going to come in and form a bond with this hydrogen, allowing your 2 carbons to reform that double bond. In addition to your chlorination and your bromination, we also looked at the nitration of your benzene. It follows the same electrophilic substitution mechanism, but in this case you're utilizing your nitric acid and your sulfuric acid to form your electrophile. So here we have the formation of your electrophile, which is your nitronium ion or your NO2 plus. So this is your nitric acid reacting with sulfuric acid is going to give you your electrophile. The same exact mechanism is going to occur whereby your electrons within your benzene ring is going to form a bond with your electrophile, breaking one of the double bonds within your benzene ring. The carbon that now has 3 bonds is carrying a +1 charge, or is known as your carbocation. In order for you to reform this double bond, you're going to have a base. Well, in this case you have a hydrogen sulfate anion coming in and taking off that hydrogen, allowing your benzene to gain max stability. So we looked at your reactions of your benzene. We looked at your methyl benzene, which is also known as your toluene. It's important to note that your methyl benzene is more reactive than your benzene ring, and this has to do with of your methyl group. So this methyl group here is electron donating or electron pushing. So it pushes the electron density onto your benzene ring, which already has its own delocalized area of electrons, making your benzene ring more negative and more susceptible to electrophilic attack. So when you're looking at reactions such as the nitration of your methyl benzene, this occurs at a lower temperature because your methyl benzene is more reactive. In terms of the products that are formed from the nitration of your methyl benzenes, once again, your methyl benzene is more reactive than your benzene. So the nitration can occur at a lower temperature. In terms of the product, you're going to end up with a higher percentage of your auto-substituted benzene ring, which is going to be on your 2nd carbon, along with your para-substituted benzene ring, which is going to be on your 4th carbon. Both of these cases are due to the formation of your tertiary carbocation, which are more stable. So again, your methyl benzene electrophilic substitution is following the same mechanism. Electrons from Your benzene ring gets donated to your electrophile, causing a bond to be formed between your carbon and that electrophile. Right? So this carbon here has 4 bonds, this other carbon here has 3 bonds, hence it has a +1 formal charge, and this is your carbocation. In addition to this, you have different types of carbocations. You have your tertiary carbocation that is attached to 3 other alkyl groups. You have your secondary, where it's attached to 2 other alkyl groups. And lastly, you have your primary carbocation attached to 1 or no other alkyl groups. Bear with me on that plus sign right there. The carbocations are more stable. Right? And because they're more stable, they're more favorable to form. So that's why you have high products in your auto and in your para. Because these, one of their resonance forms contains a tertiary carbocation. +1, that positively charged carbon is now a tertiary carbocation because this carbon here is attached to 3 things. It has a +1 charge. In addition to this, these 3 things are all alkyl groups. So this is your tertiary carbocation. Versus your meta attack, where your NO2 is substituted at your 3rd carbon. In this case, regardless of your resonance form, your positive carbocation or your +1 charge is on a carbon that is attached to 3 things, but in this case you have a carbon here, you have a hydrogen. In this case it's the same thing. So all of these resonance forms for your metal are forming your secondary carbocation, where up here you're forming your tertiary, which is your most stable. In addition to your nitration of your methyl benzene also undergoes your bromination, or you would see your chlorine being added on to your methyl benzene. In terms of the conditions for this reaction, you're gonna be utilizing the catalyst you would have utilized when you were looking at your benzene reactions, the same iron bromide or iron chloride catalyst. However, it is important for this reaction to occur in the absence of UV light / sunlight, right? So if you want your bromine or your chlorine to be attached to your benzene ring, you're going to utilize that catalyst that you met under your benzene electrophilic substitution reaction, and absolutely no UV or sunlight, right? Because in the presence of your UV light, this chlorine or this bromine is actually going to undergo your halogenation of your alkanes. Okay, so you're going to have your free radical substitution instead of your electrophilic substitution. So your free radical substitution, your halogen is being attached to your alkane, and that alkane is coming from the methyl group attached to your benzene versus your electrophilic substitution. Now we're going to be looking at your nitrobenzene. Earlier you would have looked at the formation of your nitrobenzene. This has to occur at temperatures that do not exceed 50 degrees Celsius, and in terms of forming your electrophile, you're going to be needing your nitric acid and your sulfuric acid. Temperatures are higher than 50, you're going to end up adding an additional nitronium ion to your benzene ring. So unlike your methyl group, your NO2 group is actually electron withdrawing. Right, so this NO2 group here is pulling electron density away from your benzene onto itself. This is actually going to make your benzene less reactive. Of the products being formed, your nitrobenzene is going to be mainly 3-directing or your meso-directing, meaning that your additional NO2 group is going to be on that 3rd carbon with the negative inductive effect of your NO2 plus group. And that negative inductive effect is looking at the fact that this nitrogen group is electron withdrawing in comparison to your methyl benzene, which was a positive inductive effect. Nitration of your nitrobenzene, you're going to be utilizing the same catalyst you would have utilized under the nitration of your benzene, which are going to be forming your electrophile. So you have your nitric acid and you have your sulfuric acid. However, in terms of your temperature, it has to be higher than 50 degrees Celsius. In this particular case, it's 100 degrees Celsius, and your nitrobenzene is metal or 3-directing, meaning that the majority of your product is going to be on that 1 and 3 positions. Your nitro group is carrying a positive charge. So remember, when you're undergoing your electrophilic substitution, you're going to be breaking one of your carbon to carbon double bonds. And once this bond is broken and one of your carbons end up having 3 bonds, you're going to be forming your carbocation. So in a situation where you have a positive charge here and a positive charge here, they are essentially going to be repelling each other. There has to be a position where the positive charges are far enough away from each other in order for your nitrobenzene to be considered stable. Was your auto attack, and this is your meta attack, right? So your meta is occurring at your 3rd carbon. So here you have your electrons in your benzene ring forming a bond with your electrophile, breaking that carbon to carbon double bond, right? You're going to be ending up with your carbocation or your +1 charge on this particular carbon here, or it can move throughout your benzene structure. So in either of these resonance forms, the positive charge is as far away from your nitro group as possible. So there is less repulsion in your meta attack. Just looked at the nitration of your nitrobenzene. Your other reaction is looking at the reduction of your nitrobenzene. So in terms of your reduction, this is the addition of a hydrogen to your nitrobenzene, right? And this is going to be producing your phenylamine. So in order for your reduction to occur, you're going to need your tin, and you're also going to need your hydrochloric acid. You have a nitrobenzene, you get your hydrogens from your reagents, and then you're going to be forming your phenylamine. So you have your H plus being added here, then you lose a water molecule when another H plus is added, and then the H plus goes on to your oxygen, and then when another H plus is added, you lose another water molecule. Then you end up with your NH, and then there's another H plus that is finally going to form your phenylamine. So in terms of questions, you're gonna write the product that is formed when your benzene reacts with your nitric and your sulfuric acid, and then you're gonna draw out the product that is formed when this product reacts with your tin and your HCl. This question over here asks to predict the major product being formed and give the mechanism. So here you have your nitrobenzene and you have the bromination of your nitrobenzene. One above, you're gonna draw out the structure that is needed to produce this bromobenzene here.